All right, good people. Here we are. This is the next and probably last video. Um, we have a lot of things to cover here. So maybe I'll split this into two parts now that I'm looking at what's left. Let's see. So, antiderivative rules. If we know the regular derivative rules, we just work in reverse, right? So, I'm looking for the function whose derivative will give me the sine of x. Well, we said the antiderivative of sine x is negative cosine x. Why? Because the derivative of cosine x is usually negative sine, but I'm looking for the antiderivative sign of positive sine, so therefore that's negative cosine x. The antiderivative of negative cosine x is negative sine, and don't forget plus c plus c. And then here on letter C in example 6, we have this constant. So pull out the constant and then take the antiderivative of sine x, which is negative cosine x. So that's really just going to leave you with 4 cosine x plus c. Excuse me. So a couple of things that we saw as we did those examples. Number one, if you have a constant, we can pull out the constant, right? And we can take the integral of the function that we're taking the integral of, the integrand. Second idea that we saw, if we're taking the antiderivative of a constant, then that would just be the constant x plus c. And then if it's just the integral of dx, well, then that's 1 dx, so then that'd be 1x plus c. And then if we are adding or subtracting functions and we're taking the antiderivatives, we can break it up into the antiderivative of the first plus the antiderivative of the second. And we can do it that way and break it up into little pieces. And that's what we would be doing with example 7 or 8. I feel like we've done that. Let's do one, and then maybe we'll stop and look at what's coming up ahead. Let's do letter B, actually. So I'm looking for the antiderivative of this. But this function has 1, 2, 3 pieces. So we can break it up into the antiderivative of 2 cosine x. And by the way, since I noticed there's a constant, I'm going to go ahead and write the constant in the front of the integral. Dx minus, there's another constant, so I'm going to go ahead and write it in front of the integral symbol. Now, if I pull that 3 out, the only thing that's left is 1 over x. Oh, but I can't have x's in the denominator, so let me fix that while I'm here. This will be x to the negative 1 dx. Plus, there's another constant, so 5. Antiderivative of 1 over square root of x, but I can't have roots in the denominator, so let me pull them up. That's going to be x to the negative 1/2 dx. So I want you to take a look. Everything that you see in green, that was part of a constant. That is a constant that was part of the integral or the integrand. And so I pulled it out to the front. And then make sure that you are getting how did I move this x to the top to get x to negative 1? How did I move the square root of x to the top, in order to get x to negative 1/2? Now let's take the antiderivative. The antiderivative of cosine x is sine x minus the antiderivative of x to negative 1 would be x to the, oh, wait, how does that work? X to the 0 over 0? That's not possible. Oh, you know why? Remember what the rule list said? It said that if it's 1 over x, this is the natural log of the absolute value of x. Remember, the derivative of the natural log is 1 over x. Oh, that's what I had here, 3 over x. 1 over x, then it's just the natural log. So I can't use the reverse power rule in that one situation because then I'd be dividing by 0. So I just have to remember that 1 over x is the natural log of x. Plus 5 times x to the, add 1 to the exponent, divide by the new exponent, which would be divided by 1/2, or multiplying by 2 over 1. So if I clean this up a little bit, the antiderivative is plus c. Technically, there's a plus c for each of these, but if I add all the constants together, I get one large constant that I can put at the end of my expression. And I am betting that this would give you the derivative that you see over here. Again, we kind of used all of our tricks, I should say, all of our properties of integrals in order to figure out this one antiderivative. We'll come back in the next and we'll kind of wrap it up for reals this time. For reals.